So we can see here that this is going to be a E2 reaction. Now, one of the big challenges in the course now is going to be, for every problem, deciding what type of mechanism we have, E2, E1, SN2, or SN1. There's really a bunch of factors, so the handout has a table to help you with that. So let's look at the bottom of page 3. Oops. Bottom of page 3. Okay, now the bad news is it looks like a pretty complicated table, right? But unfortunately there are some complications here for deciding what type of reaction we have. So we just have to learn how to master that table. So first of all, we have to figure out what row we're in. And you can see the row basically depends on whether we have a methyl primary, secondary, or tertiary carbon. There is one complication though, because notice that I put in 2 rows for primary hindered and primary unhindered. So we should talk about that. All right, so we're looking at the table on the bottom of page 3 of the handout. And so let's say we've got so this is what I would call a primary unhindered. So let's go back to here. Is this alpha carbon primary, secondary, or tertiary?
Primary.
Yeah, because it's attached to one other carbon chain. Now take your time on this one. How about this alpha carbon? Primary, secondary, or tertiary?
Primary.
Still primary. That's right, because it's still only attached to one carbon chain. This thing here is not attached to the alpha carbon, so this is still primary. But you can see that even though it's still primary, which of these seems like there's more steric hindrance blocking the alpha carbon?
The second one.
Yeah, because this is close enough that it can get in the way and block the nucleophile from attacking the alpha carbon. So this is what we would call primary hindered. Primary hindered basically means that even though it's still primary, there's more substituents on this carbon. Actually, let's go ahead and give this carbon a name. We're going to need this anyway. A good logical name for this carbon would be the beta carbon, right? If the alpha carbon is the carbon that's attached to the leaving group, the beta carbon is the next one over. Now, those are terms that probably your instructor won't use. They probably won't say alpha and beta, but that's really useful for clarifying the concepts here for SN2 and E2, so we'll keep using those terms. All right, so here's our alpha carbon and here's our beta carbon. So basically, then we can say for that table at the bottom of page 3, primary unhindered means that there are no substituents on the beta carbon, or few substituents on the beta carbon. And primary hindered means there's a bunch of substituents on the beta carbon. You can see this is kind of qualitative. The steric hindrance is not an all or nothing thing. You can have levels of steric hindrance, but hopefully on the exam you're not going to get close calls. You're going to get things which are pretty clear. So for example, if the instructor wants you to do an E2 reaction, they should make it pretty clear that there's a bunch of steric hindrance someplace, so that we don't have to have too much close of a call. Some of the homework problems sometimes are kind of close calls, but hopefully the exam problems won't be that subtle. Okay, so anyway, now we can see how to pick out these rows here, whether we have a primary hindered or primary unhindered, so we can pick out the right row. Does that make sense? Okay, so which of those rows at the bottom of page 3 should we be in for this compound?
Primary unhindered.
Yeah, primary unhindered. It's primary, and there's nothing at all on this carbon out here. Even if there was one, even if this was another carbon here, it would still not be very hindered. Only if there's 2 substituents here is it really going to be hindered. Okay, that tells us what row we're in. And now let's see if we can find the right column. You can see this takes practice. It's pretty confusing. There's a lot of columns, but what was our basic atom here again?
The O minus.
Yeah, good. And notice you don't want to just say O, you need to say O minus. So let's see if we can find the column with the O minus here. And you can see that those are on the right. Here's our O minus. All right, and even here there's a complication. Because then O minus could be in a bulky base or a non-bulky base.
It's a bulky base.
But here we've got a bulky base. Okay, so we're in the far right column right now. We're in the far right column, and I guess we're in the second row. All right, and what reaction do we get? Which is what we'd already predicted. This case was pretty easy, so maybe you don't need the table for this. You can kind of see bulky bases pretty much almost always give you E2. If you see a bulky base like this, you can kind of short circuit all this and say, gee, I'm pretty sure this is going to be an E2 reaction. But I want to start going through the table because there's other cases that are not so obvious. So it's important to see how to use that. Okay, so because of the steric hindrance in the base, this is going to be E2. So again, notice that first you find the right row. by looking at the substrate. And then you have to find the right column. In order to find the right column, you have to ask, what is my nucleophilic or basic atom? And you have got to get the right charge, because notice there's another oxygen all the way on the left that's neutral. And that would give us totally different reactions, or maybe no reaction at all. So I think we've talked about in previous sessions how the charges are crucial. So it's important to focus on the atom and the charge. Okay. All right. So we've decided this would be an E2 reaction. Okay. So now we're going to start going through that E2 reaction. What does the letter E stand for? Do you remember? Elimination. Do you know what elimination means?
You're getting rid of the hydrogen and the leaving group.
Okay, you're eliminating that. I'm sorry, I interrupted you.
Oh, no, that's fine.
And then you're taking those two electrons and making a double bond.
That's right.
Carbons.
That's right, exactly. So the key to elimination is that you're forming a new pi bond. An elimination reaction is a reaction that forms a new pi bond. And why is it called elimination? Because it does that by eliminating two other groups. We're eliminating the hydrogen and the leaving group, and that will give us the electrons to form a new pi bond. Okay. So let's go through the steps for that. So now then, is this going to be acting now like a nucleophile or a base? Yeah. Substitution reactions use nucleophiles, but elimination reactions use bases. So once we know this is elimination, it's a base. Well, what does a base do? We should use the Bronsted-Lowry definition of a base. What does a base do?
Deprotonate.
Yeah, it takes a proton. Now, which proton are we going to take over here? The important thing to see is we don't take the proton from the alpha carbon. We take a proton from the beta carbon. Here's where it's really useful to have this terminology of alpha and beta.
Is that in all cases?
Any elimination reaction. That's right. Any elimination reaction, you're going to take the proton from the beta carbon, not the alpha carbon. This is one of the most common mistakes people make, because this looks like a very boring carbon. There's no interesting atoms on it, but it's still going to be an important part of the reaction.
That was one of my biggest questions. I didn't understand which one you decided to use to
Right.
the.
Right. Okay. Yeah. So now we know it's the beta hydrogen. That is the hydrogen from the beta carbon. So again, try to get into the habit for all of these reactions. Anytime you're doing a substitution reaction, you should always label the alpha carbon. And anytime you're doing an elimination, you should label both the alpha and the beta carbon, because they're both going to be participating. Remember, the alpha carbon is the carbon with the leaving group, and the beta carbon is attached to it. Okay, so this guy is going to take that proton. Let's show the mechanism for that. Let's see if you guys know how to draw the correct electron pushing arrows here. So. Push it to that, like you said.
So then,
Oh, that's good.
isn't it possible too to have more than one beta carbon?
That's right, that's an issue. I don't think you guys are going to cover that issue until the final.
Okay.
So we'll see when we have time to look at the homework, but I think in this course you're not going to cover that issue until after the
Is
this
mine
section.
wrong?
No, looks pretty good to me. Yeah, keep going, see if you can draw the products. Okay, that looks good. All right, So it looks like you guys ended up with the right reaction. Now you need to practice that because you might have had some doubts along the way. Has to be something that we're very comfortable with. Now let's talk through the logic here. First of all, it should be clear that this oxygen is at the tail of an arrow because electrons are coming from it. And we know it's going to act like a base. So it's going to be donating electrons to this hydrogen over here. By the way, it's important to know the conventions for drawing electron pushing arrows because TAs can be very picky about that. One convention is that the tail of an arrow should not come directly from an atom. So in this case, the tail of the arrow should come from the negative charge, not be pointing directly to the atom. That's just a convention. But some TAs can be pretty picky about that. Okay, now that means that this oxygen is going to be forming a bond with this hydrogen. But that's going to free up the electrons in this bond because a hydrogen can't be bonded to two things. And what are we going to do with these electrons? Remember, the whole point of elimination is to form a new pi bond. So we move these electrons over here to form the new pi bond.